You know, the whole point of machine learning isn't just about showing a model what happened in the past. It's about giving it the smarts to predict the future. But there's this fundamental tension right at the heart of the whole process, a balancing act that every single one of us has to master. And today, we're breaking down that very act, the bias-variance trade-off.
Does this sound familiar? I bet it does. You train a model, you hit this beautiful 99% accuracy, and you're thinking, I've cracked it, until you push it out into the real world, and it just completely falls apart on new data. It's a classic, super frustrating rite of passage, and today, we're going to dig into exactly why that happens.
So why do our supposedly brilliant models fail? Well, it almost always comes down to two big issues. Either the model has learned way too little from the data, or, believe it or not, it's actually learned too much. Let's unpack these two classic failure modes, underfitting and overfitting.
On one side, you've got underfitting. This model is just too simple. It's kind of painting with a broad brush and completely misses the real story, the real pattern in the data. Then, on the flip side, you have overfitting. This model is like a frantic perfectionist. It's so complex, it doesn't just learn the pattern, it memorizes every single data point, including all the random, meaningless noise. Both models fail, just for completely opposite reasons. Okay, so to really fix these problems, we need to go a little deeper than just saying it's over or underfitting. We have to understand the mathematical DNA, if you will, of a model's error. We can actually break down every single mistake a model makes into a few key pieces.
Right, so every model's total error is made up of these three parts. First, there's irreducible noise. Look, this is just the random chaos in the real world that no model on Earth can ever predict. We can't do anything about it, so we don't worry about it. But the other two, bias and variance, that's our territory. These are the parts of the error we can actually control.
So let's properly introduce our two main culprits, bias and variance. Honestly, thinking of them as two distinct characters is a fantastic way to get a gut feeling for their behavior and how they mess with our models.
First up, let's talk about bias. This is the error you get from a model that's just too simplistic for the job. Imagine a stubborn student who tries to fit everything into one simple little rule. They might be consistent, sure, but they're consistently wrong because they're ignoring all the important details. This, my friends, is underfitting. And on the other side of the coin, you've got variance. This error comes from a model that's way too sensitive. It's like a nervous student who panics and memorizes every single word from the textbook, including the typos. This model gets a perfect score on the training data, but because it also memorized all the noise, it can't generalize to anything it hasn't seen before. That's overfitting for you.
Okay, so how do you actually spot this in the wild? It's pretty straightforward. A high bias model just performs poorly everywhere, on your training data and your test data. But a high variance model, it's sneaky. It looks amazing on the training data, but then completely bombs on the test data. That huge gap between the two scores, that is the classic red flag for high variance. And this, right here, brings us to the heart of the matter, the trade-off. See, you can't just get rid of bias and get rid of variance independently. They are locked in this constant balancing act. And the main lever we have to control this balance is what we call model complexity. This table lays it all out perfectly. When your model's complexity is low, you get high bias but low variance. That's underfitting. Now, as we start to crank up the complexity, the bias goes down, which is great, but the variance starts to creep up. And if you go too far, you end up with low bias but crazy high variance, and that's overfitting. Our goal is to land right in that sweet spot in the middle, the optimal fit. Visually, this creates the famous U-shaped error curve. As you increase model complexity from left to right, your total error first goes down as that high bias falls off. It hits a minimum point. That's the sweet spot we're hunting for. But if you keep making the model more complex, the error starts to climb right back up again, and this time it's being driven by that rising variance.
All right, enough theory. How do we actually find this sweet spot when we're building things? Let's roll up our sleeves and open up the practitioner's playbook for diagnosing and fixing our models.
Here is your go-to diagnostic tool. Seriously, just look at your training and test scores. Are both of them low? Bam, you've got a high bias problem. Is there a huge gap between a high training score and a low test score? Classic high variance. Are both scores high with just a small gap between them? Congratulations, you found a balanced model.
So your diagnosis is high bias? What's the fix? The core idea here is simple. You need to let your model learn more. You can do this by making it more complex, you can feed it more features, Or you can reduce any constraints, like regularization, that might be holding it back from learning the true pattern.
And if the diagnosis is high variance, well, we do the exact opposite. We need to rein the model in. This means adding things like regularization to penalize that extra complexity, or maybe simplifying the model directly, stopping the training process a little earlier, or, and this is often the best solution of all, giving it more data so it can learn the real pattern instead of just memorizing noise.
All right, let's recap the big points. Bias and variance are in a constant tug-of-war. Model complexity is the main knob we turn to manage that tension. Our whole job is to find that balance, that sweet spot that gives us the lowest error on new, unseen data. And the key to doing that is to first diagnose the problem using your train and test scores, and then apply the right set of tools to fix it.
So the next time your model isn't performing the way you hoped, don't just blindly throw more data or more layers at it. Stop and ask yourself this one simple question. Is my model being too stubborn, just failing to see the pattern? Or is it being too nervous, memorizing every little detail, including the mistakes? The answer to that question will tell you exactly what you need to do next.